So let's do module 5. This chapter is sensation and perception, basically. So module 5 is sensation, module 6 is perception. And I usually do a little exercise before I start the class, but today is only Saturday morning, so I don't want to give you sugar, so I said not today. But I usually bring the jelly beans. And what I ask is to see the color and then guess the flavor. Then you smell the jelly bean and guess the flavor. Then finally you taste it, then guess the flavor, okay? Because this is a sensation perception chapter. So you might see the color orange, then you might just guess the flavor is orange because the color is orange, okay? Then you smell it, and you smell orange, then say, yes, definitely this smell is orange. That's just sensation. You're taking the smell from your nose, then it goes back to your brain, and then comes back to your mind and say, this is orange, all right? And you taste it. Of course, your tongue is sensitive with the taste. Then you taste it, and then you say, that's orange, but I think it's mandarin orange because you tasted it. Then you see the differences, not just the regular orange, but it tastes like tangerine or mandarin orange. Then that's your perception. Sensation is the taste, but then your interpretation of the taste is mandarin orange or tangerine orange. That's your perception, okay? So those are the ones I usually use, but usually I teach the class around 11:30, so I can't give them like little sugary stuff, but it's just too early, so I decided not to give you sugar yet, okay? Well, that's the stuff we talk about today. All right. Okay, so 3 definitions. Eyes, ears, nose, skin, and tongue are complex, miniaturized, living sense organs that automatically gather information about your environment. So you use your eyes to see what's going on, your nose to smell, ear to listen, hear, okay? And skin, if you touch the hot water, yes, you feel it, and then say, oh, it's hot. And if you put your hand in a very cold ocean, you say, oh, it's too cold to jump and swim, right? That's the skin. And tongue, too, you taste it and then say, oh, it's sweet, or it's sour, it's bitter, okay? So transduction meaning process in which a sense organ changes or transforms physical energy into electrical signals that becomes neural impulses, which may be sent to the brain for processing. So for instance, you hear the noise and then transduced in your ear, and then it's gonna be a signal to send to your brain, and brain goes back to send the information back to you and then say, oh, it sounds like an ocean, or it sounds like a rain if you hear the noise, right? You usually notice that when you hear the noise outside, then you might say, do you think it's raining outside because I hear the noise? That kind of stuff. Make sense? Okay. Then adaptation. The decreasing response of the sense organs as they are exposed to a continuous level of stimulation. Can you give me an example of adaptation? Anybody? Yes?
Don't like lizards adapt and stuff like that? If it's not
Yeah, the lizard, you change the colors? Mm-hmm. Very good. Definitely adaptation because of the temperature, and then they change the color. And also, if something is coming to try to eat them, they try to change the color to protect them. Excellent. That's exactly the right example. Another one for humans, just in addition to your great example. For instance, we jump into the cold water. You feel so cold, but after like 10 minutes, oh, it's not that cold anymore. That's another example of adaptation. Make sense to you? Very good. So, sensation versus perception. Relatively meaningless bits of information that result when the brain processes electrical signals that come from the sense organs. Then perceptions, meaningful sensory experiences that result after the brain combines hundreds of sensations. So for instance, okay, you drink wine, all right? Sensation is, it tastes good. But then perception will be, this must be Pinot Grigio. Make sense to you? Perception meaning you analyze your sensation and then get more detailed information. Or for instance, you eat, let's say, sushi, all right? Then your sensation is, oh, it tastes actually not bad. It tastes like, let's say, chicken, for instance. Then not taste part is your sensation, but then the perception part is tastes like chicken. I have to give you an example. I have a friend, she's a very close friend of mine, and she came to Japan to visit my house. So she stayed, and then my father and I took her to a sushi place, and also like a little nice Japanese restaurant. Then we gave her blowfish. You know what blowfish is, right? It's poisonous, but only the chef who has a certificate can cut the poisonous part and then, serve it. And then it's called delicacy in Japan, okay? So, of course, she doesn't want to eat raw fish, so I asked the chef to cook it, although it's blowfish. So she tasted it, and she loved it. She said, it tastes like chicken, I like it. And then after she ate it, I said, actually, Lauren, it was blowfish. Her face turned like pale. But then she said, but it tasted good. Did I really eat blowfish? So I said, yes, you did. So like this, sensation and perception. Make sense to you? Very good. Awesome. Okay. So another one, eye. Vision is the most exclusively studied sense organ in psychology, okay? So stimulus is the light waves. And then we have visible and invisible light. Invisible light is too short, like for instance, gamma rays, X-rays, ultraviolet rays. You can't see it. But visible light, particular segment of electromagnetic energy that we can see because these waves are the right length to stimulate receptors in the eye. So, for instance, the colors you see, it's the visible colors and visible light. And the colors can be created by the combination of different lights. Okay, I'll explain more. So another invisible light. The waves are too long, so those are you can't see. For instance, the radar, FM radio, TV shortwave, and AM radio too. Those are the waves that we use, but you can't see the lights, basically. All right? I'll explain more, so don't worry about it. So here we go. So long wavelengths and then short wavelengths. And the visible lights are only that much compared to those wavelengths, the long wavelengths and short wavelengths. It's between about 400 to 700 nanometers. Those are the visible lights we see, okay? So, eyes perform two separate processes. And you have to remember, eye is like a camera without the film. That's how the eye works, okay? So first, gather and focus light into precise area in the back of eye. Then area absorbs and transforms light waves into electrical impulses. So this process is called transduction again, okay? Transformation from the visible light to electrical signals again, okay? Or impulses. All right, so 7 steps. Image reserve, light waves, cornea, pupil, iris, lens, and retina. All those anatomy of your eye, but it's not the biology class again, so we just go through it quickly. But I explain more about psychology stuff. So, in the back of the eye, objects appear upside down, okay? And then somehow the brain turns the object right side up. That's what the brain works, okay? Then light waves are changed from broad beams to narrow focused ones, okay? And cornea is the rounded, transparent covering over the front of your eye, and pupil is the round opening at the front of the eye that allows light waves to pass into the eye's interior. Iris, the circular muscle that surrounds the pupil and controls the amount of light entering the eye, and lens, transparent oval structure whose curved surface bends and focuses light waves into an even narrower beam, okay? And retina is located at the very back of the eyeball, a thin film that contains cells that are extremely sensitive to light. And light-sensitive cells, called photoreceptors, which I will talk about a little bit more, begin the process of transduction by absorbing light waves, okay? So this is it, like upside-down image, the giraffe, right? But then somehow it goes back to the right side, okay? So retina is at the back of the eye, right there, okay? So we have 3 layers of cells, okay? Back layer contains 2 kinds of photoreceptors that begin the process of transduction, change light waves into electrical signals, as I told you. Rod located primarily in the periphery. Cone located primarily in the center of the retina called the fovea. And those 2 are the most important ones among the anatomy of eye that you should remember, all right? So rods, okay, photoreceptor that contain a single chemical called rhodopsin, okay, activated by small amounts of light. So very light sensitive, allow us to see in dim light and see only black, white, and shades of gray. So for instance, at home, at night, okay, you're sleeping, but you got thirsty, so you get up and then go to the kitchen to have a glass of water. When you wake up, because it was dark in the room, you can't see well. But you can still go to the kitchen, get the glass of water. You might hit your ankle with on the corner of the room or something like that because you can't see well. But when you do that, you are using rods because you can't see the colors. But and then less spatial information, but you can still see somehow, right? That's called using rods, okay? On the other hand, cones, okay? Photoreceptors that contain 3 chemicals called opsins, activated in bright light, okay? So right now, you're using cones, not rods. You see my color today? What color do I wear today? Blue and black and some silver lines, right? You're using cones to see the colors, okay? Allow us to see color. Cones are wired individually to neighboring cells. Allow us to see fine detail too. You see my shape, you see my hair color, everything, okay? But if it's in the dim light, if it's dark here, then you can't see me well, but you kind of know that where I am, okay? But no fine details, okay? Good. And then, again, visual pathways, eye to brain. We use optic nerve, primary visual cortex, visual association areas. Okay. So basically, this is your left eye. And then left side is related to the right side anyway. And the right side of the brain is related to the left side. The same thing with eyes, too. And we have crossover right there, but I explain later. Okay. So optic nerve impulses flow through the optic nerve as it exits from the back of the eye, and then we have the blind spot, meaning you can't see, all right? Then the optic nerves partially cross and pass through the thalamus. The thalamus relays impulses to the back of the occipital lobe in the right and left hemisphere, as you learned from last week's chapter or lecture, okay? Then primary visual cortex, back of the occipital lobes, is where primary visual cortex transforms nerve impulses into simple visual sensations. Then visual association areas, primary visual cortex sends simple visual sensations to neighboring association area. Then damage to the visual association area, meaning visual agnosia, difficulty in assembling simple visual sensations into more complex, meaningful images. All right? But you don't have to worry about that, okay? All right, so making colors from wavelengths. How do we do this, okay? Sunlight is called white light because it contains all the light waves, okay? So white light passes through a prism, separates light waves that vary in length. It's all about length, 400 nanometers to 700 nanometers, okay? Visual system transforms light waves of various lengths into millions of different colors. So shorter wavelengths of violet, blue, green. So like 400 nanometers is more like blue oriented. Then longer wavelengths of yellow, orange, and red. So as going towards 700 nanometers, it's more warm color like red, orange, yellow, okay? An apple is seen as red because the reflection of longer light waves that brain interprets as red. Then we have green apple too, okay? But we can distinguish the colors because of the length of the lights, okay? Like that. As you can see, 400 nanometer, it's more violet color, and then blue, green, yellow, and red. So that's how we transform the lights to wavelengths, okay? And color vision too. You watch TV, you see all different colors, right? Okay? But we have trichromatic theory, meaning 3 different kinds of cones in the retina. We have 3 cones, but 1 rod, okay? Because rod is colorblind, remember? We can see black, white, gray, but no colors, all right? So each cone contains one of those 3 different light-sensitive chemicals called opsins. Each of the 3 opsins is most responsive to wavelengths that correspond to each of the 3 primary colors. And what are they? The 3 primary colors are blue, green, and red, okay? All colors can be mixed from these primary colors. So you watch TV, you see all different colors, right? But you know what? TV has only 3 phosphors. That's blue, green, and red. And they manipulate our system, visual system, as we are seeing all different colors. Did you guys know that? That's what they do, okay? Very good. Then another one is called opponent process theory, after image, okay? Visual sensation that continues after the original stimulus is removed. So ganglion cells in retina and cells in thalamus respond to 2 pairs of colors, red, green, and blue, yellow. Okay, when excited, respond to 1 color of the pair. When inhibited, respond to complementary pair. All right, so another one is called color blindness, inability to distinguish 2 or more shades in the color spectrum, okay? Monochromatic, total color blindness, only black and white. Result of only one kind of functioning cone, okay? Dichromatic, meaning inherited genetic defect, mostly in males. So color blindness is more common among males, not females, all right? Trouble distinguish red from green. 2 kinds of cones see mostly shades of green. So if I had like images, okay, and it's red color, but the number was 74 in the middle, and it's green. If you're not colorblind, you can see, yes, the number is 74. But if the person is colorblind, he cannot see the numbers. He just say, I just see all red. Okay. One of my students had color blindness. So I asked him in class. He didn't mind. He said, I don't see the number. That's interesting, okay? But he can see red, but he can't really see green colors. All right? Okay, very good. All right. Then ear. Sound waves, stimuli for hearing. Ripples of different size, sound waves travel through space with varying height and frequency. We have amplitude and loudness, okay? Height or frequency, okay? Height, distance from the bottom to the top of the sound wave, amplitude. Then frequency, number of sound waves occurring within a second. So those two, amplitude and frequency, okay? Loudness, okay? Subjective experience of a sound's intensity. Brain calculates loudness from specific physical energy. Okay, amplitude of sound waves. Pitch, on the other hand, subjective experience of sound being high or low pitch. Okay, brain calculates from specific physical stimuli. Speed or frequency of sound waves measured in cycles. How many sound waves in a second? Okay. All right. So, how to measure sound waves? Okay, we have decibel. You need to measure loudness. Then we have threshold for hearing. Okay, meaning the little, like smallest thing that you can detect. Okay, that's called absolute threshold. And 0 decibels meaning no sound, but 140, pain and permanent hearing loss. So, for instance, how many of you have been to like a loud concert, like a rock concert or something like that? And next day or so, you might have a hard time like hearing other people, right? That's related to that because you heard loud sound for a long time, like 2 hours or 3 hours. The next 2 days or so, you have a hard time listening, okay, because of the loudness, all right? Pitch too sometimes. All right, so for instance, this one. Oh, this is a good one. So threshold hearing meaning 0. So you really don't hear the sound of very small sound, like whispering right here, 30 decibels. Whisper, quiet, library, gasoline-only car, idling in neutral. That's kind of noise. So it's quiet, basically. Then conversation, air conditioner at 20 feet, okay. Then heavy city traffic, alarm clock at 2 feet, subway, MP3 player or iPod. So if you use iPod, that's the level of the sound, okay. Then chainsaw, jackhammer, baby screaming inside of racing car, pretty much loud. So if you expose for 2 hours or more can cause hearing loss. Workers using light power tools who do not use ear protectors risk hearing loss. So you see the workers wearing the stuff, right? So they don't cause any trouble with their ears, okay? Then rock concert near speakers, thunderclap, record set in human ear. Exposure for only 15 minutes or less can produce hearing loss. Rock musicians and fans who do not use earplugs risk hearing loss. Okay? Then the loudest is jet engine, gun muzzle, blast, firecracker explosion. So any exposure to sounds this loud is painful and dangerous. That's why aircraft ground personnel must wear ear protectors. Okay? All right. All right, so outer, middle, and inner ear, it's just anatomy of ear again. So outer ear consists of 3 structures: external ear auditory canal, and then tympanic membrane. That's not biology, well, it's not the biology class, I'm not gonna go through it much. Then external ear is oval-shaped structure that protrudes from the side of the head and function pick up sound waves and then send them down the auditory canal, okay? And you know what's going to happen, right? Long tube that funnels sound waves down its length so that the waves strike the tympanic membrane, eardrum, and then transduction starts, okay? All right. Sound waves strike the tympanic membrane and cause it to vibrate. So the sound is transformed to vibration to send the information to your brain, right? Okay, that's what happens with ear. Right there, you hear the sound, my lecture, and then going into the inner ear and then transduced to the hair bending, and then vibration goes through that, okay? All right, the middle ear, okay? Bony cavity sealed at each end by membranes that are connected by 3 tiny bones called ossicles, okay? Let's talk about balance a little bit, okay? So, position and balance. Vestibular system is located above the cochlea in the inner ear and includes semicircular canals. So bony eggs set at different angles, and then each canal is filled with fluid. Okay, we have fluid in the ear too, of course, right? That moves in response to movements of your head, basically. Okay. So includes sensing the position of the head, keeping the head upright, and maintaining balance. That's I can stand like this, and I don't lose the balance, right? Make sense? Okay, very good. All right, the motion sickness. How many of you have motion sickness? I don't. Can you read when you are in like a train or in the car? Some people get sick when they do that, okay? So that's called motion sickness, okay? So symptoms, feelings of discomfort, nausea, and the dizziness in the moving vehicle. Head bouncing, but distant objects look very steady too, okay? All right, the other ones, don't worry about it. Then taste. So when you eat the food, you taste the differences, right? If you eat like chocolate, what taste do you sense? Sweetness. If you take the bitter chocolate, you sense bitterness, right? All right, what else? If you eat lemon or grapefruit, what taste do you sense? Sourness, right? Very good. So you use your tongue to taste, all right? So this is a chemical sense because the stimuli are various chemicals. So you use tongue. Surface of the tongue, okay, is responsible for different taste, okay? I explained taste buds. Everybody has taste buds, right? Okay, good. So 5 basic tastes: sweet, salty, sour, bitter, and umami. Meaty, cheesy taste. Interesting. Umami means yummy, like yummy taste, all right? All right, so among those 5 basic tastes, which one do you think we sense the most or first? Sour, you think it's sourness? The tip of the tongue is related to the sweetness. And then maybe the side is more related to, I believe, was either salt or bitterness. Salty or bitter taste. But the tip of the first thing you taste is the sweetness, basically. That's why babies prefer sweet taste to begin with. All right? Good. Isn't that interesting? Yeah. All right. So, surface of the tongue, okay? Chemicals which are the stimuli for taste break down into molecules. And molecules mix with saliva and run into narrow trenches on the surface of the tongue. Then, molecules then stimulate the taste buds. All right? Good. So, taste buds shaped like miniature onions. And those are the receptors for taste, okay? So chemicals dissolved in saliva activate taste buds and produce nerve impulses that reach areas of the brain's parietal lobe. And then brain transforms impulses into sensations of taste. So flavor combination of taste and smell. So when you eat, you smell the food, you taste the food, and it tastes really good. All right, that's what happens. Very good. Then smell, okay? Steps for olfaction, stimulus, olfactory cells, sensation, and memories, and functions of olfaction. Some of the people, they smell something like the cologne and say, that reminds me of my father when I was a young girl, something like that. So the smell can recall some memories too, like that, okay? Taste too. When you taste something, how many of you have seen the Disney movie Ratatouille? Like the mouse makes the, yeah, remember that? And then this guy, the food critic, his name was Ego or something, right? Yeah, egocentric, that's why, but it was a funny movie. But when he tasted the food, he dropped the fork or spoon, and the mouse made the ratatouille. It's like a very simple vegetable dish in France, but he dropped the spoon or fork because it reminded him of his mother's cooking. All right? So the smell and taste can bring some memories back like that. All right? Very good. All right, so you smell, oh my God, that's skunk. But skunk definitely has a strong smell. When I'm driving, I smell it and say, oh my God, that's skunk. Then it smells bad for like 10 seconds. Then still we can smell a tiny bit, but we're going away, but it's very strong smell, as you all know, okay? So that's how we smell. Senses, those smell is transduced to as the chemical, right? Or what do we call it? Oh, the system. Anyway, you know that, okay? All right, so stimulus. We smell volatile substances. So those are released molecules in the air at the room temperature. So examples, skunk spray, perfumes, warm brownies, not glass or steel. Yeah, you smell the baked cookies, and it smells so good. And then although you are on diet, you might want to taste it because it smells so good, right? All right. Brownies too. All right. So receptors for smell located in a 1-inch square patch of tissue in the uppermost part of the nasal passages, right there. The olfactory cells are covered in mucus that dissolves volatile molecules and stimulates the cells. The cells trigger nerve impulses that travel to the brain, which interprets the impulses as different smells. Then memories, okay? So nerve impulses travel to the olfactory bulb. Then impulses are relayed to the primary olfactory cortex, and cortex transforms nerve impulses into olfactory sensations. Then we can identify as many as, believe it or not, 10,000 different odors. Can you imagine that? We don't think about it, but we can distinguish like that many different smells, okay? We stop smelling our deodorants or perfumes because of decreased responding, adaptation. The first time, of course, it's a strong smell, but you get used to it, and then you're not paying much attention anymore. Make sense to you? Okay, very good. Then, functions. One function to intensify the taste of food. Second function to warn of potentially dangerous foods. Warn, okay? And third function to elicit strong memories, emotional feelings too. It's related to chapter 5 or modules 9 and 10, okay, classical conditioning. If you smell the food that it made you sick before, then that brings your memory being sick. Then it might make you sick again. That's related to this, but I'll explain in modules 9 and 10, okay? All right. And touch includes pressure, temperature, and pain. Beneath the outer layer of skin are a half dozen miniature sensors that are receptors for the sense of touch. All right. So change mechanical pressure, temperature, vibrations into nerve impulses that are sent to the brain for processing. Okay. Okay. So those are the nerve cells. That's the skin. Okay. Then you have hair like that, right there. Okay. So underneath, many sensors there. So receptors in the skin itself, hair receptors, free nerve endings, and Pacinian corpuscle. Okay. So skin, outermost layer, right there. You have all skins, right? All right. So thin film of dead cells containing no receptors. Just below are fast receptors, which look like groups of thread-like extensions, and middle and fatty layer, and a variety of receptors with different shapes and functions. Some are hair receptors too. It's just the biology here too. Okay, and hair receptors, free nerve endings wrapped around the base of each hair follicle. And then they fire with the burst of activity when first bent. And if hair remains bent for a period of time, the receptor will cease firing. Then sensory adaptation occurs. Remember, we talked about it. If you put yourself in the cold water and after 10 minutes, you're used to it. It's not as cold as you thought at the beginning. So wearing a watch too. When you put the watch first, you have a sensation there. It's heavy, it's cold. But then after like 10 minutes, you forget that you're wearing a watch, right? The same thing. Glasses, if you wear glasses, when you put it on, you're like, oh. But after like, sometimes I put my glasses on my head and I said, where's my glasses? Where are they, right? Same thing, all right? So going back to the pain, all right? Unpleasant sensory and emotional experience that may result from tissue damage, one's thoughts or beliefs or environmental stressors. So it can be caused by our thoughts or beliefs or even environmental stressors. Like if you're stressed out about like this class, you might have a headache or you might have stomachache because you are stressed out. That's possible, okay? So pain results from many different stimuli, okay? All right, so pain signals coming from spinal cord reach the brain. Remember the spinal cord, okay? Back of your brain and then goes down to basically bottom, like hip, okay? Then with gate open, we feel pain right there, okay? But pain signals coming from spinal cord do not reach the brain. Gate is closed, then you don't feel pain. That's how it works, all right? So how does the mind stop pain? Gate control theory of pain. Non-painful nerve impulses compete with pain impulses in trying to reach the brain. Then creates a bottleneck or neutral gate. And shifting attention or rubbing an injured area decreases the passage of painful impulses. Result, pain is diluted. That's this theory says. So for instance, one of my kids, the other day, she fell down at the playground. And she cried, but I was like rubbing her skin. I'm like, it's okay, it's okay. After a minute, she started running away, okay? Running around again, okay? Then after 2 days, she had black eye here. But then she said it's not bad, okay? So it's possible to take the pain away like that, okay? Endorphins, of course, chemicals produced by the brain and secreted in response to injury or severe physical or psychological stress. So this one is going to kill or reduce the pain. Pain-reducing properties of endorphins are similar to those of morphine. You know how morphine works, right? Okay. So brain produces endorphins in situations that evoke great fear, anxiety, stress, or bodily injury, as well as intense aerobic activity too. So after you run so much, you rest, you feel high, basically. That because the endorphins are produced even more, that you will be not feeling pain much. Makes sense to you? Because the chemical, the endorphins is produced more, so the pain doesn't reach you much. Or if the pain is there, it can be much lower than usual. Make sense? Okay. And dread. Connected to pain centers in brain, not the act itself that people fear, but time waiting before event causes dread too. So if you're supposed to do the public speaking, you get nervous, right? Then you might feel pain there because of the stress. Acupuncture. Trained practitioners insert thin needles into various points on the body's surface and then manually twirl or electrically stimulate the needles. After 10 to 20 minutes of stimulation, patients often report a reduction in various kinds of pain. Okay. Acupuncture works for some people. Okay. So that was module 5, but I'm gonna go on to module 6 because it's chapter 3. Okay. All right. So perception. Any questions so far? Okay. This part is more psychology, okay? Perception is more psychology than sensation. Sensation is more biological oriented, okay? But threshold, a point above which a stimulus is perceived and below which it isn't. Threshold determines when we first become aware of a stimulus, okay? So, absolute threshold, I explained tiny bit in module 5, but the intensity level of the stimulus such that a person will have a 50% chance of detecting it. So for instance, if I drop the cologne just tiny bit right at the end of the classroom, you might be able to still smell it. That's absolute threshold, okay? Okay. So subliminal stimulus has an intensity that gives a person less than a 50% chance of detecting the stimulus. Okay. So for instance, breast cancer detection, accuracy problems, looking for ways to lower the threshold for detecting cancerous tumors and thus saving patients' lives. Recently, use of digital mammograms allows for images to be enhanced or magnified. It's better in detecting cancerous tumors in women. Okay. So basic differences again. Sensations are first awareness of some outside stimulus. Activate sensory receptors, which in turn produce electrical signals that are transformed by the brain into meaningless bits of information. Then perceptions. The experience we have out our brain assembles and combines thousands of individual sensations into a meaningful pattern or image. So perceptions are based on your experiences. So you might let's assume that we all went to the Fenway Park to see the baseball game, Red Sox game. And we had, let's say, beer and hot dogs. Okay, I like Coke and hot dogs, but I'm just making up the story right now. Your perception can be different based on your experiences. You might like eating a hot dog and beer at the Fenway because the ballpark, you have a nice childhood memory that you went to the game before, all right? And then you like beer. Then the beer tasted good. And the hot dog tasted even better because you're eating at the Fenway Park. That's related to your perceptions of what you experienced before. But on the other hand, let's say some of you got sick with hot dogs before. So you went to the Fenway Park and then had beer and then hot dog. But because of your past experience being sick, you don't want to eat it. You don't want to touch it. So you ate something else rather than hot dog. That's related to your perception too. Make sense to you? Very good. So, how do we change sensation into perception? We talked about this, but it's like a summary. Stimulus change of energy into the environment, like waves for visual information, sound waves for the ear, and the mechanical pressure or chemicals for like pain and then taste. Transaction changes physical energy into electrical signals, and those are changed into impulses that travel into the brain, and the brain impulses from senses first go to different primary areas of the brain because different areas of brain is related to different functioning, as you might remember from the last class, okay? So, brain is the association areas, and sensual impulses are sent to the appropriate association area in the brain. Then each of us has a unique set of personal experiences, emotions, and memories that are automatically added to our perceptions by other areas of the brain. And it's just so quick that you don't even think much when it happens, okay? Then structuralists said, they believe that you add together hundreds of basic elements to form complex perceptions. On the other hand, Gestalt psychologists believe our brains follow a set of rules that specify how individual elements are to be organized into a meaningful pattern of perception, okay? This is more psychology, guys. So this is the interesting one too. Organizational rules, okay? Gestalt psychologists specified how our brains combine and organize individual elements into a meaningful perception. So we have figure and ground, okay? This one, figure and ground. Basically, we have two images. We have one picture, and then you might see the base or two faces facing at each other. If you saw two faces facing each other, if you first saw it and that's the one you see it, it means that's the figure. The ground is the base. And if you saw the base first, that's your figure, and two faces are a ground. I explained to you after the break too. I bring the image back, okay? So, and the similarity meaning in organized stimuli, we group together elements that appear similar, okay? I'll bring the images, so don't worry about it. Closure too. In organizing stimuli, we tend to fill in missing parts of a figure and see it as complete. Proximity. In organizing stimuli, we group together objects that are physically close to one another. Simplicity. Stimuli are organized in the simplest way possible. Continuity. We favor the continuous path when interpreting a series of points. So for instance, intersections with highways. That's called continuity. All right, I'll explain more with the images after the break. All right, then shape, size, brightness, and color constancy. Size constancy meaning our tendency to perceive objects as remaining the same size even when the images on the retina are continually growing or shrinking. So for instance, you see me in the distance, but you know that oh, there's Professor Arai. You know it. And as I get closer, my image will be bigger because I'm getting closer. Then I say hi to you. I walk away, and my image will be getting smaller and smaller and smaller because I'm distancing from you, right? That's called size constancy. Although I look bigger towards you and I look smaller away from you, my size is constant. I don't change my height or weight, right? It's the same. But the images can be smaller or bigger based on the distance too. Shape constancy refers to a tendency to perceive an object as retaining its same shape even when we view it from different angles. So you see the big tree, and in different angles, then you might think that it looks different, but it's the same tree, right? Okay, very good. Then brightness constancy too refers to the tendency to perceive brightness as remaining the same in changing illumination. Color constancy refers to the tendency to perceive colors as remaining stable despite differences in lighting. Okay. And depth perception. ability of eye and brain to add a third dimension, 3D depth, to all visual perceptions, even though image is projected on the retina are in only 2 dimensions, height and width. Okay, so if you see some certain movies with the special glasses, you looks like the object can come out of the screen to just jumping onto you, right? So we kind of manipulate our visual system to see those 3D images, because without those special glasses, we only see 2Ds, all right? So binocular or binocular depth cues depends on the movement of both eyes. Convergence, meaning binocular cue for depth perception based on signals sent from muscles that turn the eyes, okay? So like that. Okay, and then retinal disparity, okay? Refers to the binocular depth cue that depends on the distance between the eyes. Each eye receives a slightly different image. So cover your left eye right now with your hand and see this screen. Then move towards the right eye to cover your right eye. Do you see slightly difference? That's called disparity. Okay? So difference between left and right eye's images is retinal disparity. So brain interprets large retinal disparity close object as small retinal disparity distant object. So it's the same thing, but it's slightly different, right? Makes sense to you? And if you wear glasses, your eye, you know, when you measure your how good your eyesight is, it can be slightly different too, because we are independent, right eye and left eye. The same thing, we have disparities right there, like we have blind spot. Okay, very good. Do you see that? We have crossover right here. Okay, and then the blind spot in between 2 eyes, we can see, right? Okay. So monocular depth cue, mono means 1. So we have linear produced by signals from only a single eye, only right or left. So linear perspective meaning monocular depth cue that result as parallel lines come together in the distance. So relative size, the results when we expect 2 objects to be the same size, but they aren't. Okay, so for instance, there are a series of like trees. As you walk towards the tree, okay, you know that the sizes are the same, but from the distance, you might think that the closest is the tallest, and then going shorter and shorter, right? Okay, so interposition meaning the monocular depth cue that comes into play when objects overlap too, okay? So we have different illusions too. And light and shadow, okay? Monocular depth cues where brightly lit objects appear closer while objects in shadows appear farther away. Okay, and texture gradient meaning monocular depth cue in which areas with sharp, detailed texture interpreted as being closer, and then those with less shapeless and poorer detail are perceived as more distant. So because of the distance, you can see more details, and then farther down, you can't see the details much. Okay, it's just the depth cue. Okay, then atmospheric perspective, monocular depth cue created by the presence of dust, smoke, clouds, or water vapor. Okay, and motion parallax, monocular depth cue based on the speed of the moving object. So you see the race car going, right? And then of course the dust, smoke too, the clouds. Okay, moving object. Okay, illusions. Okay, illusion meaning a perceptual experience in which you perceive an image as being so strangely distorted that in reality it can't and doesn't exist. Okay, so impossible figure, perceptual experience in which a drawing seems to defy basic geometric laws too. Do you see the illusion here? What do you see? Dots. If you stare at it, what's going to happen?
They are moving.
Yeah, as if they're moving, right? Okay? All right. Okay, and the subliminal message. Brief auditory or visual message presented below the absolute threshold. I'm sorry, I can't say that word. Means a less than 50% chance that the message will be perceived. Have you seen subliminal message before? Very short, like even you cannot retain much information, but basically your brain tries to capture it. So self-fulfilling prophecies involve having strong beliefs about changing some behavior and then acting unknowingly to change that behavior. So if, although you don't believe in that, you might be buying it and then saying that, yes, okay. So what's the good example of self-fulfilling? Okay, so if someone says, all right, because you're community college students, the classes should be easy. Someone says that. Then you start believing that, yeah, community college, taking a class at community college should be easy. It's not, but you're buying it and then you're believing that information. That's self-fulfilling, okay? Okay. Then extrasensory perception. Group of psychic experiences involve perceiving or sending information or images outside normal sensory processes or channels. So we have 4 general abilities. Telepathy, okay. Ability to transfer one's thoughts to another or to read the thoughts of others. So schizophrenic oriented, okay. And then precognition, ability to foretell events. Like something will happen like that, okay. Like sixth sense, all right. So that was module 6.